Good morning, folks. We have been talking some about atomic structure, and we are just now getting into looking at electrons and how electrons are arranged. Just kind of as a disclaimer before we start, you can take pretty much anything you think you know about how electrons move around the nucleus of an atom and sort of chuck it out the window. Okay? Electrons do not move in nice little circular or elliptical orbits round and round the nucleus of an atom. That's a handy way of thinking about it when you're first teaching little kids about atoms and about the parts that are inside there. But when it comes to their actual behavior, that kind of model breaks down. And it has to give way to what is now our modern understanding of how the atom works. And to be totally honest, there is still a heck of a lot we don't understand about how atoms and electrons work. So, we're going to start just by kind of recapping what we know about electrons and how we got there. We know that electrons have a negative charge. We also know that they're super tiny. The reason why we don't bother looking at the mass of electrons when we're taking the mass of an atom is because it would take about 2,000 electrons to get the mass of just one proton or one neutron. And there's no atoms that have 2,000 electrons. So it's negligible. It's almost not there. We know, based on experiments that have been done on atoms, that electrons reside outside of an atom's nucleus. Can anybody recall for me the name of the experiment where they first learned that electrons were a thing? I'll give you a little hint. Cathode ray tube experiment, very good. We had these glass tubes, which they filled with a low pressure gas. They had a positive and a negative electrode hooked up to it, and they ran electric current through it, and it made the thing glow. And they also noticed that it gave off little particles that were flowing from the negative end over to the positive end. They weren't sure if they were particles, though. They could have just been rays or waves or something. And so, if you remember, they changed it up and they put a little glass paddle wheel in the middle there. And then when they turned it on, something was smacking into the little paddles on that wheel enough to make it turn and spin. So they figured that, well, electrons have to be particles. Except that they don't always behave like particles. And let me give you a for instance. Let's say that I had a wall with some holes in it. And I pointed some electrons, beams of electrons, at that wall, and I shot them toward it. Now, if they were particles, what you would expect to see is you would expect to see those particles continue straight up until they ran into something. Okay, because that's what particles do. Particles kind of like a tennis ball. I throw a tennis ball, I expect it to go in a more or less straight line, minus whatever gravity and air resistance does to it, because that's what it does. But that's not what happened. Instead of getting little patterns of electrons whenever they tried to do this, they would instead get these really weird, wacky patterns that looked a little bit more like bullseye targets. And the only thing that could really explain that is if instead of acting like particles, that those electrons would get to these little holes and then they would start spreading out. They would start bending around the corner. Particles don't bend around corners, but do you know what does? What if I draw it like this? Can you tell me? Rainbow, no.
Electrons?
Waves. And so electrons behave like waves as well as behaving like particles. They have a finite mass, meaning that you can't actually measure the mass of one. They measured the mass of the electron in the oil drop experiment, And so we know it has a finite mass, whereas a wave does not have a finite mass. A wave is just energy moving through something, but then they behave like waves. And so it was obvious that we really had to kind of change our perspective on what electrons were if we were really going to understand and predict how it is that they behave, how it is that they move. And so they had to invent a whole new branch of science just to describe electron behavior, and it's called quantum mechanics. And the most important word on this entire slide is this one right here. We're going to talk about 4 different rules or principles that dictate the behavior of electrons. Now, every year for UIL Science, they put out a book that you're supposed to have your students read, and they take a certain number of physics questions from that book. Last year's book was this guy right here, okay, How to Teach Quantum Physics to Your Dog. I read maybe about halfway through this book, and I just kind of had to give up because I didn't get it, okay? So I hope that dogs are smarter than I am, because there is some weird, spooky stuff that electrons can do. Electrons can move through solid surfaces. Electrons can actually be entwined, meaning that they are in tune with other electrons, and then you can separate them to pretty much infinite distances, and if you change something that happens in one, it causes a change in the other one. How do they know this? Okay, electrons can both exist and not exist at the same time, which is not something that makes sense to us. And so when you get into talking about quantum physics, it gets weird. That's all I'm going to say. We're not going to get into too much of the weirdness or too much of the math behind the weirdness here, but just understand electrons are bizarre. And what we're trying to do here and what we'll try and do in this class is try and make sense as best we can of some of their weird, spooky behavior. But the important word to keep in mind there is probable, not certain. Probable. The first of the different rules we're going to take a look at is something called the Heisenberg uncertainty principle. It was authored by I believe he was German scientist named Werner Heisenberg. I'll probably edit that out. Maybe. Those of you who are a fan of Breaking Bad, this is where he got his little alias name from this guy. Heisenberg said that because of the spooky, weird behavior of electrons, it is impossible to know both an electron's position and its velocity at the same time. Now, before you write that down, just hear me out for a minute. What that means is that electrons are always in motion. This much we know. But if you observe an electron in a particular place, by the time you have made that observation, it has already moved on to some other place. And so I can know where it is, but if I know exactly where it is at a given moment, I can't know where it's going. Or I might know its velocity. I might know about how fast and in what general direction it's moving. But if I know that, I can't at the same time know where along that path it's going to be. Okay? There is uncertainty built in. Now, deep cut for all of my nerds, or all of my casual nerds, TV show Star Trek that's been around since like the 60s. One of the things that they do on this show is instead of like having to fly down from their ship to the planet all the time, they can do a thing where they can like beam you down or beam you up. Okay. Basically, they've got this thing called a transporter, and what it does is it records every molecule in your body. Okay, where it is, what it's doing. It takes a snapshot of that. It changes you into energy, shoots the energy somewhere else, and then puts you back together again. okay, atom by atom, particle by particle. The problem with that is Heisenberg's uncertainty principle. I can't know where every particle is and where it's going at the same time. So maybe you could take me apart and all my particles and then shoot them somewhere, but you wouldn't be able to put them back together again the way that they were. And so at some point in the show, the various, Star Trek folks working on the ships, they've got a thing called a Heisenberg compensator that's part of all their transporters. And I'd love to see how one of those things works. But anyway, because we can't know exactly where it is and exactly where it's going, what we deal with is probability. Okay? Not certainty. We deal with probability. We can say, okay, an electron could be anywhere. But based on things we know about it, we can predict where it's most likely going to be found at any given time. Now, we've already touched on this a little bit when we were talking about atomic spectra. When you looked at those little tubes of hot gas and you looked at them through your spectroscope, it got separated out into different little colored lines, right? What's happening is that those are giving off. Remember, you got those electrons that get excited and they jump way up and then they fall back down to different levels, and when they fall down they stream and give off that light energy. Well, it's, instead of saying just a wide broad spectrum of color, meaning that they can jump from anywhere into anywhere, what that tells us is that they tend to spend most of their time at certain distances from the nucleus, and they tend to jump between those certain distances. Okay? Instead of it being like a slide, it's really much more like a staircase. Okay? So the electrons are going to be more likely to be found on this step or on this step or on this step instead of somewhere in between. This is a decent place to ask a question if you have one. Okay, so first rule, Heisenberg. Okay. The next rule, why are you on my next page? That's weird. The next rule is what's called the Aufbau principle. And I also like to refer to this as the glass of water principle. And here's what I mean by that. Let's say that you take a glass and you're going to pour water into it. So if I've got my pitcher, I've got my water, I'm going to pour it into this glass. And I pour it in the glass and I notice that the water rests up at the top of the glass and leaves the bottom empty, right? Mm-hmm. Yes, that's what happens? No. I don't know what y'all are smoking. That's not what happens at all. Where does the water go when you pour it in the glass? It goes to the bottom and it fills the bottom. And then if I add more water, it fills up from there until it gets to the top of the glass. And the reason why water goes all the way down to the bottom of the glass is what? Gravity. Okay? We talked about potential energy before, and how when you've got gravitational potential energy, the closer to the Earth something is, the less energy it has. And it will tend to be in a low energy position. The only reason that this water up here at the top isn't down there at the bottom is what? Because there's already water there, right? It's already taken up space. Electrons are exactly the same way. And I'm going to explain what I mean. Instead of a glass of water, what we've got is a series of three-dimensional regions called energy levels. Okay? Now, if you imagine that instead of down here, underneath the glass of water, you've got Earth, what we've got down here underneath these energy levels is the nucleus of the atom. Okay? Now, as you move up from there, you're going to come to a region of space outside the nucleus where it's the first major energy level. And if I have electrons going around that atom, they're going to get as close to that nucleus as possible. Okay? They're going to fill up that lowest energy level, and then once there's no more space for electrons, if I have more electrons, they're going to get added to the next higher energy level, and so on and so forth. This right here doesn't make any sense to you. It will make sense to you by the time we're done. This right here actually accounts for more electrons than we have atoms that would fill it. Okay? The biggest discovered atom we have so far is element number 118. Element number 118 would actually stop right here. Okay? And so all these other electrons up here, we don't even have atoms that get that big. Not yet. Okay? We may invent some in the future. That would be fine.
It wouldn't be very stable though, right?
Well, the ones that they've got up to that point haven't been. Their hope is that at some point they're going to find, quote unquote, an island of stability in some of these artificial elements where we will have stable elements. And a lot of that will have to do with the nucleus. A lot of that will probably have to do with how the electrons are arranged. Okay? But who knows? I wouldn't, because one, you're going to have video. Two, I'm going to probably hand this out to you at some point later on. No, please don't draw that. That's crazy sauce. There's way too much there. Like I said, don't worry so much about the particulars of this yet. We will get to them. We're just not to it yet. So, Aufbau principle. Electrons will fill the lowest energy levels before they start filling higher ones. The third principle is what's called the Pauli exclusion principle. What does it mean to exclude someone or exclude something? Right, not include them, right? Don't let them in. Don't invite them. Okay? The Pauli exclusion principle means that in a region of space around an atom in an energy level, there's only so much room for electrons to fit. And then once it runs out of room, no two electrons can fill the same space at the same time. So if electrons have to share a space, then they can't have the same energy.
Teachers, please pardon the interruption.
Sure.
Axel Martinez, could you please return to Ms. Henshaw's room? Axel Martinez.
All right. Good times. We'll talk more about this, especially after tomorrow. But we refer to kind of a packet of space where an electron can exist as an orbital. And it doesn't look like a little box, but we symbolize it with a little box. And two electrons can share that space. We symbolize the electrons as little arrows. Now, what do you notice about the two little arrows in this box up here?
Opposite directions.
Opposite directions. What that indicates is that they have opposite energy. Okay? One of them has what's called a positive spin, and one has what's called a negative spin. And that has to do with kind of the direction that they're going. But see, because of Heisenberg, we don't know what direction they're going. We can't be certain. And so when you examine the spin on these electrons, we say that one of them has a spin of plus 1/2 and one has a spin of minus 1/2. But since we don't know which one's which, if they're paired up, then we say that they've got a spin of plus or minus 1/2. It's either one or the other. Or, because quantum physics, maybe it's both until you observe it, and then it's going to be one or the other. Oh, did I tell you that? That simply observing a particle like an electron changes its behavior?
Really?
It's like they know they're being watched?
That's weird.
Yeah, I'm telling you, it's bizarre. Yeah, I got a few copies, and if you want to check one out and borrow it, that's fine. Okay, we'll talk. But like I said, it's a stiff read. I mean, it's entertaining because the guy talks to his dog and the dog talks back, but it gets really deep really quick. So that's the Pauli exclusion principle. Pauli exclusion principle says that the place an electron takes up is exclusive, meaning two electrons can't be in the same space, going the same way at the same time. It's kind of like my hand and this wall cannot occupy the same space at the same time, and if I try and make that happen, it hurts, okay? Because we can't both be there at the same time. It is exclusive to its space, and I'm exclusive to mine. Okay. Next one's one of my favorite rules. It's called the Hund's rule. I refer to this as the guys in a bathroom rule. See, and the funny thing about that is that pretty much every guy instantly knows what I'm talking about, and the girls are all like, what's he talking about?
Yeah, I was like, what?
Okay, so here's the thing. Ladies, guys, I'm sorry. Gentlemen are going to have naturally a better understanding of this instinctively than you will, because I know when you go to the bathroom, it's like a social event, okay? You take all your friends with you, you talk, you take selfies, you paint your nails. I don't know what all happens in there. I really don't want to know, okay? It's kind of like electrons. It's spooky, and I don't understand it, so I'm just going to leave it alone. But see, guys, when they're in a public restroom, it's a little bit of a different thing. Gentlemen, do this math problem for me. If you have 2 men in a public restroom, how many men too many is that? 1 or 2, right? Okay? Because guys do not like to share bathroom space, and I don't exactly know why. I have a theory that maybe we feel our most vulnerable when we're doing our business, and so if someone's going to like attack and kill us, that's going to be where it's going to happen. You know, we're going to literally get caught with our pants down. Okay? And so, Hund's rule says that electrons will exist 1 per orbital until every orbital has 1 electron, and then more will be filled later. Okay? But in a nutshell, let me kind of show you what this looks like in a picture here. So let's say you've got a public restroom, okay? Now, please listen, this is not a perfect metaphor. It kind of falls apart a little bit when you start picking at it, but let me show you what I mean. So, let's say that you've got the door to a public restroom right here, okay? Now, you walk in this public restroom, and there are 3 urinals, okay? So, when a guy first enters this public restroom, gentlemen, which urinal is he going to step to?
You could do the middle and mess everyone up, so that can help.
Okay, all right. I'm going to agree that unless you're just trolling, you're probably going to go to this one right here at the far left, okay? And the reason you're going to do that is because it's going to give you more distance from you to the door. That way, if someone else comes in, you've got more time to prepare for an attack. Okay? Now, second guy walks in the bathroom. He sees the first guy sees him. Now, instantly there's some tension. And that's because guys here are a lot like electrons. They have a negative charge. And if you bring 2 negative charges close together, what do they tend to do? No, they don't fight. They push each other away. They repel. Exactly. Electrons, according to the glass of water principle, they want to be as close to the nucleus as possible, but at the same time, that's where the other electrons are, and they don't want to get too close to the other electrons, so they get pushed away. So, guy number 2 entering this restroom would go to which urinal?
Right.
The one as far as possible from him, right?
Yes.
Now here's where the metaphor falls apart. Because an electron is actually going to come to the next urinal, okay? I guess electrons are a little more secure in their manhood than all the rest of us are. I don't know what the deal is. But anyway, it's going to come to this next one. In real life, the guy would actually step up to this urinal and do his business. And when guy number 3 walks in the bathroom, we got problems, right? Because he can either stand and wait and pretend they don't exist, you know, and look at his shoes, or, you know, he's probably going to do what I would do. He's going to go try and find a bush outside somewhere, okay? But if he steps in between these, there's more tension because the electrons are repelling each other. Now, like I said, it's not a perfect metaphor. So instead of looking at guys in a bathroom, we are going to look at electrons in orbitals. So the first electron it's going to get, if the nucleus is over here, it's going to get as close to the nucleus as possible. There it is. The second electron is also going to be drawn close to the nucleus, but it's not going to want to get super close, so it's going to end up in the next orbital. Third electron coming in will end up in the next orbital over. Now, a fourth electron enters the scene. Where is it going to go?
Nowhere.
Oh, it has to go somewhere.
That's the way.
It's going to come to the first one, but it's going to have an opposite spin. Like I said, we're out of the metaphor now, and we're dealing back with electrons, okay? Guys don't do this unless they're like 4 years old and they're having a contest. Okay? And gentlemen, again, you know exactly what I'm talking about. But electron number 4 is going to come in here because it's being drawn to the nucleus, and even though it's being pushed away from these, this is the least repellent solution because at least it's close to the nucleus. Electron 5 would get dropped here. Electron 6 would get dropped here. Now, what if electron 7 shows up?
It gets dropped.
It goes to the next side, goes up.
It keeps
Great.
going up.
There's no more room in this bathroom.
Oh.
So it's got to go find another orbital at a higher energy level. Okay? You kind of with me here?
Yeah.
I promise you it'll make more sense after the next few days. But for right now, let me kind of set this out of the way. So let's do just a real quick walkthrough. Okay? If I've got the element hydrogen. Hydrogen has atomic number 1. So how many electrons does hydrogen usually have? 1. Energy level 1 is closest to the nucleus, so this 1 electron, where is it going to end up? It's going to end up in energy level 1. Okay? Helium has 2 electrons usually. Where will its second electron end up? It will end up sharing this energy level. Now at this point, energy level 1 is completely full. And so we go up from there, we hit lithium. Lithium is element number 3, 3 protons, usually 3 electrons. The first 2 are going to be right here. The third electron is going to be right there. Okay? Beryllium, element number 4. Fourth electron is going to end up right there. Now, sublevel 2s is now full. And so we have to move up to the next sublevel. Now this is a bigger bathroom. There's 3 urinals here. Okay? And so we get into boron, element number 5. 1, 2, 3, 4. The first 4 electrons are in level 1. And then this first part of level 2. Okay? There's boron. Now it's only when you really get to carbon, element number 6 or bigger, that Hund's rule kicks in. Because the 6th electron is going to go where? It's going to go to the next stall, right there. Okay? And I'm going to be sure and maybe put a little note by that. Okay, this would be electron 6. I'm going to see it with carbon. Or bigger. So then after carbon, we get to nitrogen. 7 electrons. First 2 go here. First 2 go here. 5, 6, 7. Oxygen. First 2, 5, 6, 7. Number 8 comes back here. And then fluorine, number 9. Neon, number 10. Well, what happens after you hit number 10? Then you go up to the next highest energy level. Because this energy level 2, is completely full. So let me ask you this. How many electrons can fit in that first energy level total? 2. How many electrons total can fit in the second energy level? 8. The whole energy level includes both of these bathrooms here. Okay? Anybody want to guess how many can fit in the third energy level? I haven't drawn the whole thing here.
Oh, 9.
16, 20, 32.
18.
Oh.
Okay? Because energy level 3 has a little bathroom like this. It has a slightly bigger one like this, and it's got an even bigger one with 5 stalls where electrons can go.
Okay.
So as you go out, now this also makes sense. Let me show you why this makes sense. If you've got the nucleus of an atom, let's say the nucleus of an atom, let's get where we can see it on the time. Nucleus of the atom is right here. So there's a roughly spherical region of space around that. Okay? And it would be a sphere. It would come out. I can't draw in 3D. That's why it only looks like 2D. That's going to be our first energy level. So here's energy level 1. It can hold 2 electrons. Now there's going to be a bigger sphere outside of that. The bigger sphere outside of that, no? bigger one outside of here, this is going to be energy level 2. It can hold 8 electrons. Why? But, I mean, looking here, why could it hold more electrons?
Bigger.
Say again, Hayden?
It's bigger.
It's bigger. There's more space for it. Now, energy level 3 is even more chungus than this. Okay, so it can hold a total of 18. And it gets bigger as you go up. There is more to it. You will understand more about it, but for right now, we're going to skip on to, I think that's all of our rules. Do we have any rules after that one? No, that's the guy. That's it. So, that takes us to the end of today's lecture on electron arrangements. Now, I would like you guys to ask me 2 really good questions before we put away. Yeah.
How big can it get to? Like, if you go from 2 to 8 to 18, like, what's the biggest?
Okay. Let's see. Okay, so the 4th energy level. One second. 3rd energy level can hold 18. 4th energy level can hold 18 plus 14. So 4th can hold 32. The 5th can theoretically hold more than that, but as far as we know, there's only atoms that hold 32 beyond that. Okay? Hey, everybody keeps moving around. I did not say move around and put stuff up. What's your really good question, Rain?
Do you have to put a thing in and everything? Like, I don't know.
Okay.
Like, you have to put.
You mean, could I leave a blank space here and just go on to the next one?
Yeah.
Under normal circumstances, no. That would be like pouring water into the glass and there being a bubble where the water's in. Okay? Under special circumstances, sometimes yes. But usually not. We'll talk about the special circumstances when we start getting into Vesper theory and start talking about molecule shapes. That's coming up in a few weeks. Okay. All right. So good class, you guys. And tomorrow, when you color your periodic tables, you will find out why the shape of the periodic table makes more sense than you ever thought it did before. And for some of you, the big click is going to happen tomorrow. If it doesn't tomorrow, it will happen Thursday when I do that.